Okay, now that we've introduced the property of entropy, we want to get into our second law equation, which is an entropy balance. We're first going to look at a closed system, right? So it's got the same amount of mass being acted on the whole time, okay? Go back to our second law statement, and we actually have one specific to entropy, and that statement states that it is impossible for any system to operate in a way that entropy is destroyed, okay? So that's another way to frame the second law, and that leads to the main equation that we're using for a closed system for the second law, and that is given here, where I have S2 minus S1, which is the change in entropy. These are the properties of the system. This is what I'm looking up in the tables. Now remember that these properties are coming from this equation, okay? So again, it doesn't have a huge physical meaning, okay? So I'm pulling that entropy change from the tables. Okay. Then I have that entropy transfer that accompanies the heat transfer across the boundary. Okay, so that is that heat transfer divided by the temperature at the boundary that it occurs at. Now it's got an integral sign, but for most of our purposes, this is going to be kind of an isothermal, or it'll tell you what the boundary temperature is. So there won't be much integrating going on here. The final term here is the entropy production, which is really the measure of irreversibility. That's our sigma value. This is the one that has to be greater than 0. Now, again, the entropy transfer, the first term on the right side of the equation, the Q over T, again, this accompanies the heat transfer. It's in the same direction as the heat transfer. So if there's heat transferred to the system, generally there's going to be entropy transferred to the system. Heat transferred from the system, there's going to be an entropy transfer from the system. Okay, and again, that sigma term, that's my entropy production. Okay, and again, this is the measure of irreversibility. So if it has to be greater than 0. Okay, because real systems have irreversibilities, it has to be 0. Okay, if sigma equals 0, that's a reversible system. So again, we've talked about this idea of an isentropic process, right, where it's an adiabatic reversible system. So if it's adiabatic, again, Q goes to 0. If it's reversible, sigma goes to 0. That means S2 minus S1 equals 0. That's a constant entropy situation. So adiabatic and reversible leads to an isentropic or a constant entropy sort of process here. Okay. Now, this entropy production is, again, the measure of the irreversibilities. Okay. The actual value, again, we don't have a strong idea. There's not a strong physical correlation between entropy and, the physical world. However, it's useful in comparison. So say you've got a power cycle, you can do each process in the power cycle, find sigma for each process, and from that figure out which device is the most irreversible, and fixate on that and try to improve that performance. It gives you a place where you can devote time to make better, because as that approaches 0, the better your performance is going to be. Okay. Now, keep in mind, sigma has to be positive. However, the change in the property, entropy of the system, can definitely be negative. Okay. That is, S2 minus S1 can be negative. Sigma has to be positive, excuse me. The property change can be positive or negative. An example of this is if I have a large heat loss, that is a large negative Q, okay, then, and say it's a reversible process, that negative Q, again, we just talked about how that entropy transfer follows that, which means I'm going to have a negative change in entropy along with that. Okay, so sigma has to be positive, but again, that change in entropy, the property change, can definitely be negative. So this is the second law equation for a closed system.